All right, thanks for coming, everyone. Today we have the pleasure of having David Torregrossa Belén, who's a postdoctoral fellow at Center for Mathematical Modeling at the University of Chile. He works in optimization and convex and variational analysis with a special emphasis on the design of numerical methods. In 2024, he got his PhD under the supervision of Professor Francisco Aragon. And during his postdoctoral training, he completed research stays at the University of Vienna and University of Waterloo.
Okay, so thank you. Okay, thank you very much for the introduction. Well, so yes, it was just said when I was doing my PhD, I spent like 2 years here in Waterloo. I had very good memories from that time, so I'm very happy to be able to be here again. And also I would like to take a moment to thank Henry and also Walla for hosting me whenever I ask them. So yeah, so my talk today is going to be about optimization. And since I think that the audience is very heterogeneous, I want to start by saying a few words about optimization. And I like to understand the main goal in optimization as the search for a best element in a collection with respect to some criterion. And perhaps the easiest way to express this mathematically is as this optimization problem here, where we want to minimize some function over some constraint set, which is C. And here, like this set C is going to be representing the collection of points that we want to consider, and then the criterion that we want to improve or get the best element for is going to be given by the function f. Okay, so in general, when we minimize this function over this set, we are getting this best element in the set. So this is like probably the easiest way to see this, but in practice, the problems that we face in practice look more like this. So this is a problem in image recovery, and it's not important right now what are the different things that appear here. Maybe if I have some time later, I will explain further about them. But what I want you to see is that this problem is given in the same way than this one here. The set here is a box constraint, and then our function f in this case is all this term here. That the thing that I want to convey is that it doesn't have a simple structure, but it's given by different terms, and each one of these terms has different properties. And when we want to solve this numerically, it's important to be able to take advantage of the properties of each term. So it's not useful to consider all this as a single function. Okay, so this is related to the methods that I was working during my PhD, which are called splitting methods, that specialize in addressing these challenging structured problems by iteratively solving simpler subtasks that can be defined with different parts of the original problem. So the idea would be to try to solve minimization problems involving different parts of these or these terms separately in order to obtain the final solution. Yeah, so this is what I want to talk about you today, and I'm going to give some introduction because I'm not sure if you're familiar about them, and then I want to focus in one problem that I was addressing in the first years of my PhD. Okay, so first, let me start by fixing some notation. So I'm going to consider some functions through the talk, which are going to be defined in some Hilbert space, H, real Hilbert space, and that takes value in the extended real line, which is the real line, and can also take values between the values minus infinite and plus infinite. But I'm going to assume that these functions are going to be proper, which means that they never take the value minus infinite, actually, and at least at some vector they take the value, a finite value. And also, these functions I'm going to assume then that they are lower semi-continuous, which means that Well, this is a one-sided version of continuity, so the definition is given here. If you have this equality here, then you would have continuity, but we just need that the limit is greater or equal than the value of the function at the point. Okay. So this happens to be a node optimization because what this gives you is that the epigraph of the function is closed, which is the property that you require. And then finally, I'm just always assuming that today I'm just going to talk about convex optimization. Okay, okay, so I'm not sure if you're familiar with all these functions, but so let me just give one example of why this is the functions that we consider. So suppose that we want to minimize some function phi, which is finite valued, over some set which is closed and convex and non-empty. Okay, so you have this problem, which is a constraint problem. And in general, maybe it is not convenient to have to deal with the constraint independently. Okay? So what you would like is to try to deal with the constraint in terms of a function too, and then you can do that by defining this indicator function, which is denoted as iota c, which takes values 0 if the point x is in the set C, and otherwise it takes the value plus an infinite. So this function is an extended real valued function that takes value here, and it happens to be proper because the set is non-empty, so there's always one point at which the function takes the value 0, and it's also lower semi-continuous. So by using this function, then this constraint problem here is equivalent to this other unconstrained problem where you have the sum of the original function that you wanted to minimize and this indicator function here. And it's very easy to see that these problems are equivalent because whenever you consider a point x here that is evaluated in this function f, then if x is not on C, then the f is going to take the value plus infinite. So you ignore this point for your problem. And otherwise, if x is in C, then this term is equals to 0. So the value is the same as the original problem. Okay? So any question until this point? Okay. So now I'm going to start talking about the splitting methods. And as I said, this is a class of methods that you want to use to solve complex problems. But for starting, I'm just going to start with a very simple case where I just want to minimize some function which is proper over semi-continuous and convex. So I guess that you're familiar with Fermat's rule, at least in the case when your function is differentiable. Then what you usually do if you want to minimize a differentiable function, you just compute the gradient and equal to 0, and if it is convex, then you get the minimizer. Okay, but here we don't have in general differentiable functions, so what we have is some generalization of Fermat's rules that tells you that if a function, the x is a minimizer of a function, if and only if it is a 0 of the subdifferential of the function. So this means that 0 belongs to this operator, which is the subdifferential evaluated at the point x. And here is the definition of subdifferential, if you are not familiar with it, which is it's a set-valued operator that, given a point x bar, maps in all these vectors u, that what they do is that these vectors u are going to define hyperplanes that leave the epigraph of the functions above them. Okay, so for example, for this example here, -1 would be a subgradient because it belongs to the subdifferential of f at this point x bar. So as I said, it is set-valued because the subdifferential can have multiple images. So for example, the point -2 would also be a subgradient, would also belong to the subdifferential because this other line also leaves the epigraph above. And then this generalizes the gradient also, because if, for example, we go to this part of the function where it is differentiable, then the only element of the subdifferential will coincide with the gradient of the function, which is giving you the tangent line to the function. Okay? And then what the Fermat's rule here is saying us is that in order a point x bar is a minimizer if and only if you can find some horizontal hyperplane that leaves you all the epigraph of the function above. Okay, so this is the idea. Okay, so the convex subdifferential has two very important properties. The first one is that it is monotone, that it's given by this, which is the generalization of the fact that the gradient of a one-dimensional differentiable function, convex differentiable function, sorry, is monotone non-increasing. So this would be the generalization of that. And then the second property is that it is maximal, which means that there are no other, is this expression here, okay? So the fact is that if you have a pair of points in the space such that this monotone inequality is verified, for any other pair of points in the graph of the subdifferential, then the point that you consider in the first place should also belong to the graph of the subdifferential. Okay? So what we do when we work with splitting algorithms is that we just don't focus only on subdifferentials, but we consider a more general class of operators which are called the maximally monotone operators that are given, are defined in this way. So if you have some set valued operator A, you say that it is monotone if it verifies the first property, and it is maximally monotone if it verifies the two properties. Okay, so in particular, the subdifferential of a convex function would be a maximally monotone operator. Okay, so the thing is that then it turns out that the problem of minimizing a function is equivalent to the problem of finding a zero of a maximally monotone operator, and then this is going to motivate us to consider the following problem, that is the one that I'm going to talk about through the rest of the presentation, that is, given a monotone operator in principle, we don't need maximally, we want to find a zero of this operator. Okay, so this is called the monotone inclusion problem. So as a first approximation to this problem, let me just do the following. So assume that you have a zero of the problem, this point x bar, then the definition tells you that zero belongs to the image of A at x bar. So I can sum x bar at both sides of this expression, and I get here, this is the identity operator. So, and this is equivalent to saying that if x bar belongs to the image of the identity plus A at x bar, then x bar also belongs to the preimage of the identity plus A at x bar. And this thing that we have here has a name. It's a very important operator which is called the resolvent of A. Okay, so it's given in this form. I'm gonna use J to denote the resolvent. Okay, so there is one property of this operator that is that it is single valued whenever A is monotone. So now here what I have is this is an equality, and then what I can say is that the problem of finding a zero of a monotone operator is equivalent of the problem of finding a fixed point of its resolvent. Okay? And there is also another property that has resolvent operator, and is that it has full domain if and only if the monotone operator A is maximally monotone. Okay, so in practice, this tells you that since we want splitting algorithms that will be defining the whole space, then it is important to consider the resolvents of maximally monotone operators. Okay, so actually what we care about are maximally monotone operators. Okay, so before continuing, just going again to the optimization case. So if the A is just the subdifferential of a proper lower semi-continuous convex function, then the resolvent is nothing else but the proximity operator of F, that I think that you might be familiar with it if you have been studying some course on continuous optimization. And then this equivalence that I just gave here is actually corresponds to the equivalence between the set of minimizers of a function with the set of fixed points of the proximity operator. Okay, so now we had our problem of our monotone inclusion, and we said that it is equivalent to finding a fixed point of an operator. So then if you want to find a fixed point of an operator, what is useful to do is consider a fixed point iteration. And this is what one of the most famous algorithms in optimization which is the proximal point algorithm, that in order to solve the monotone inclusion, it considers the fixed point iteration of the resolvent operator. So it's given in this way. I just included here some additional parameter, which is a positive parameter gamma, which is the step size. So right now it is not, I just want to say that the set of fixed point of this operator with gamma is equal to this one here. And if I have time, I will say why this parameter is important, okay, at some moment. Okay, so this algorithm was studied first by Martinet in the case of optimization, and then for monotone operators by Rockefeller, and the convergence result says the following. If the operator A is maximally monotone, you need maximally here, and then the set of zeros of A is non-empty. This is, you have, the problem has a solution. Then the sequence xk that generates converts weakly to a fixed point of A. And the proof of this result is based on fixed point theory. So let me give you some definitions about that. So whenever we have a single valued operator T, we say that it is non-expansive if it is Lipschitz continuous with constant 1. Okay? So then, so here a problem arises, and is that if you think of the most famous result for fixed point iterations is the Banach-Picard theorem. And for that one, what you really need is your operator to be a contraction. And a contraction, it has to be Lipschitz constant strictly less than 1. Okay? So it happens that for the operators that we appear in this kind of problems, you don't have, they are not a contraction, so you cannot apply the Banach-Picard iterations. So you need something else. And you can do one trick, that is that, okay, so let's consider the convex combination of a non-expansive operator and the identity. Then this kind of operator is called alpha average non-expansive, where alpha is this parameter between 0 and 1. And it turns out that for this class of operators, then you have some fixed point result, and which is called the Krasnozelski-Man iteration, that guarantees the convergence to the weak convergence to some fixed point of non-expansive operators whenever the set of fixed points is non-empty. Okay? So it turns out that the resolvent of a maximally monotone operator is average non-expansive. So in order to get the previous result that I showed you in the previous iteration, you can just replace T by the resolvent, and then you have that the proximal point algorithm will converge weakly to some point in the set of fixed points of the resolvent that I showed you like 2 slides before, that it coincides with the set of zeros. So then you would have you are able to solve the monotone inclusion problem. Okay? So that was the case for one operator. So what happens if we have a more complicated problem and now we want to minimize the sum of 2 convex functions? Okay? So then, in order to solve this, under some conditions, you can write this problem as the problem of finding a zero of the sum of the subdifferential of these functions. Okay? And since the subdifferentials are maximally monotone, then it makes sense to consider another more general monotone inclusion problem, which is given 2 maximally monotone operators A1 and A2, find that zero of its sum. Okay? So then, so in general, the sum of 2 monotone operators is also monotone, so you would think of, okay, let's also apply the proximal point algorithm to solve this problem. Okay, so, but there is a problem. The first is that, in general, the sum of 2 maximally monotone operators is not maximally monotone, so that's the first thing. And the second thing is that, in order to apply the proximal point algorithm, you need the resolvent of the sum of the 2 operators. And it turns out that resolvents are not, in general, not easy to compute, and in practice what you have is like some selection of operators that you know how to compute their resolvents, and then you can only use those. Okay? So you don't want to try to get resolvents of the sum because maybe you don't have formulas. Okay, so, but there is one alternative, and the alternative is to try to use the structure of the problem and maybe propose some algorithm that instead of using the resolvent of the sum can use the resolvent of A1 and A2 independently. Okay, and this is, again, the idea of splitting algorithms. Okay, so you have a complicated problem with different elements, and instead of addressing all them together, you address them separately. Okay, and in fact, this is what one of my favorite algorithms does. That is the Douglas-Lushford algorithm. So it takes this form. So the important thing here is that you have the resolvent of the first operator here and the resolvent of the second operator here. They are separate. Okay? And then the convergence theorem of this method was given by the effort of several authors, and it says the following, that whenever you have two maximally monotone operators and you have a solution to the problem, then the governing sequence, which is the sequence set k here, will converge weakly to some point set bar, but it turns out that this point is not necessarily the solution of your problem, but this other sequence xk, which is the one that you obtain after applying the first resolvent to the governing variable, then this one is going to converge weakly to the resolvent of A1 at the point set bar, and this one is the one that is going to give you a solution to the monotone inclusion problem. Okay? Here I gave the algorithm in this way, but if I just replace xk, this xk here, then I can rewrite the Douglas-Lushford operator instead of this Douglas-Lushford operator, which is this operator here, and then you can see that the Douglas-Lushford also is given by a fixed point iteration, okay, of some of this operator T dr. Okay, and then the proof of this result is also based in fixed point theory. Oh, sorry, and then I can also say that this point set bar is going to be a fixed point of the Douglas-Lushford operator, so we now know what is it. Okay. Yeah, so the proof is also based on fixed point theory, and it's given by the fact that the Douglas-Lushford operator is also average non-expansive, but there is one difference with respect to the proximal point algorithm, and it's that the set of fixed points is not equal to the set of solutions to the problem, to the set of zeros of the sum. Okay? But there is still one relationship, and is that if you map the set of fixed points by the first resolvent, then you do get the set of zeros. Okay? So I want to give you one illustration of how this algorithm works. So this is the expression that I just showed you, but in order to show this picture, I think it's better if I just work in terms of the reflected resolvent, which is this operator Ra, which is 2 times the resolvent minus the identity. Then the Douglas-Lushford operator has a different expression, which is given in this way, which is you first perform the resolvent of the first operator, the reflection onto the first operator, then the second reflected resolvent, and then you do the average. And then, so what I'm going to show you is the Douglas-Lushford applied to a feasibility problem, which consists in finding a point in the intersection of these two balls, which is only given by one point here. Okay, so then it turns out that the maximally monotone operators that we care for this problem are the subdifferentials of the indicators onto each one of the balls, and then the resolvents are going to be the projections onto the balls, and the reflected resolvents are just going to be the reflections onto the balls. Okay, so if I perform one iteration of the Douglas-Lushford starting from this point at 0, the first thing that I'm going to do is reflect onto the first ball, then I'm going to reflect onto the second ball, and then to obtain the next point in iteration, I'm just going to do the average between these 2 points, and this set 1 is going to be the next point in the iteration. So if I continue my iteration, then what I get is that the governing sequence, the sequence of the sets, is going to converge to some point here, which is not in the intersection, but whenever I do the first resolvent, which in this case is the projection onto C1, then I do get the point in the intersection, a point in the set of zeros, okay? Okay, so now let's go with a more complicated problem. What happens if instead of just having two maximally monotone operators, I have n maximally monotone operators, then I want to find the zero of each sum. So there is one very simple trick, which is known since the 70s, I think, which is, in order to apply this, it is called the peerless product space reformulation, which consists in applying Douglas-Rashfords to a special choice of operators, which is this operator volt A, which is like a Cartesian product of all the maximally monotone operators appearing in the sum, and then this operator, which is the subdifferential of the indicator function of this set delta n, which is the diagonal subspace. Okay, so the important thing here is that these operators are defined in Hn, which is the n-fold Cartesian product. This is, we need m copies of the original variable to evaluate them. And when I apply Douglas-Rashford to them, what I get is this iteration here, which again uses the resolvents of each one of the maximally operators independently. Okay, so it's in the spirit of splitting algorithms. You also get weak convergence to a set of zero, but just applying the same result for Douglas-Rashford. Okay, but there is one thing here, and as I said, since these operators are defined in this space, in order to perform this iteration, what I need is to initialize my algorithm in this space here, in Hn. So I have n copies instead of one, which is the previous case. Okay, so then, and what I want to say here is that this is a problem, and let me illustrate it with one very simple example. Okay, so what happens if, again, I go back to the case of two operators, then I have two methods to solve this problem, the Douglas-Rashford operator, and then the peerless product space reformulation, which was the previous slide, applied to this. Then these are the two methods, and if I compute their iterations, then they are not only different, but if you can see here, I could write this in only one line, but the peerless product space reformulation, I had to write it in 2 lines, because I need 2 variables to compute this method. Okay? So in general, the Douglas-Rashford operator, or the Douglas-Rashford algorithm was given by a fixed point of this operator, which was defined in H, but peerless product space reformulation is defined by this other operator defined in H2. So broadly speaking, this is what we call lifting. We say that Douglas-Rashford has 1 for lifting, while the product space reformulation has 2 for lifting. Okay, so then we can understand of the lifting of an algorithm as the dimension of its ambient space. And then one of the problems that I was interested in when I was doing my PhD was in studying this lifting. And the thing is that in general, you want to have a lifting as small as possible. Okay, so let me give another example to illustrate this. So as I said, the lifting is given by the dimension of the ambient space of the algorithm. So why do you want it to be small? So for example, I have one image here, and imagine that I have one, I'm interested in getting some experiment in image processing or whatever, and the thing is that this image here has this number of pixels of width and this number of pixels on height. So if I identify this with one vector, it will be given by one vector in R to this power here, which is almost 2 million. Okay, so this will be the space H where the variable that I'm considering for my algorithm. So then if my algorithm has D for lifting, this means that the space where the algorithm is defined is H to the power D. Okay, so then at every iteration of the method, what I'm updating actually is D times these almost 2 million variables. Okay, so then if you want to reduce the memory requirements of your method, then you want D to be as small as possible, because then it is expected that your algorithm will perform better, okay? So, but this is just the idea. Actually, there is no result, as far as I know, that like theoretical result that says that it is true, but we could validate it with some experiment that I hope to have time to show you, okay? But yeah, so the thing is that what I was interested and what other authors have been doing lately is try to study this lifting and try to say which is the minimal lifting that we can get, and also get some algorithms matching this minimal lifting. Okay, so this is what the rest of my talk is going to be about. So I need to give some, in order to present this problem, I need to fix some more notation. Okay, so in the following, I'm going to be interested in this monotone inclusion, where I have, again, n maximal monotone operator, and I want to find a zero of its sum. So from what I told you, I hope that we can all agree that whenever I talk of a splitting algorithm, I can kind of encode this method, or this method can be given by two operators. The first one is going to be a fixed point operator T, which is the one that is going to be define the fixed point iteration of the method. But then I need a second operator, which is a solution mapping S, which is the one that it's going to allow me to recover a solution of the monotone inclusion problem. Okay, so this was what happened for the Douglas-Lushford operator. So then I'm going to call a fixed point encoding to such a pair of operators for the monotone inclusions if the following is satisfied. The first thing is that the set of fixed points of the operators is non-empty if and only if the set of zeros of the problem is non-empty. So there is one relationship between the problem that I want to solve and the operator that I'm going to use to solve it. And then if given some solution of the fixed point, or some fixed point of the operator, then I can recover a solution of the monotone inclusion problem by applying the solution mapping. Okay? So here is the rigorous definition of lifting, which says that a fixed point encoding has default lifting if both the fixed point operator and the solution mapping are defined in the default product space, okay? Cartesian product. Okay, so in general, D will represent the number of copies of variables needed for evaluating both T and S. Okay? So, well, just to gather the previous examples into this definition, so for the case n equals 1, I presented the proximal point algorithm, which has one for lifting because their fixed point operator was the resolvent of the maximally monotone operator, and the solution mapping was just the identity. For n equals 2, I had the Douglas-Lushford operator that also has one for lifting because T was the Douglas-Lushford operator that I could write in just one line, but then I needed this solution mapping, which was the resolvent of the first operator, because I needed to apply this to get the solution of the monotone inclusion. But then for n equals greater than 2, then what I had was peerless product space reformulation that gave me an algorithm with n for lifting, since both T and S were defined by D in this way, but where these operators that appear here and here were given by in this space. Okay, so I had. Okay. So then let me now write D star n to denote the minimal lifting that a fixed point encoding can have for a monotone inclusion with n operators. Okay, so the problem that I'm interested in now is to determine some lower bound or determine this value for the minimal value for, a lower bound for Dn, okay, and then devise some fixed point encodings or some splitting algorithms that match these bounds. Okay, so so different authors got some results. So the first ones are the following. So for the case equals 1, n equals 1, and the case n equals 2, you know that the minimal lifting is 1 because it cannot be less. And we had that both the proximal point algorithm and the Douglas-Lasford verified those bounds. So for n equals 3, Liu was the first that in 2020 proved that the minimal lifting has to be 2, and he also proposed what is the so-called Liu's splitting, which had 2 for lifting. Okay? And then for the case n greater or equal than 3, then Malitsky and Tamp gave the result that the minimal lifting had to be n minus 1, and also gave one algorithm that had this lifting. Okay, but there is one disclaimer here, is that in the result, they did not allow the use of step size parameters in the resolvents. Okay, so the step size parameters are these parameters, gamma, that I included before. And there are 2 things. It's convenient to include these parameters when you consider splitting algorithms. The first one is because there already were algorithms that with different parameters in the resolvent had the minimal lifting property and was not included in the result. So according to the result, there could be like algorithms that had less lifting when you add these step sizes. And the second thing is that for another kind of monotone inclusions that I hope to have time to talk about, you need these parameters to control some of the elements of the problem. So then what we did was, the first result that we got is we extended the result to splitting algorithms that included parameters in the algorithm, in the evaluation of resolvents. And in order to do that, we needed some rules, which are the following. So we consider a special class of splitting algorithms, which are the so-called resolvent splitting, which namely is that both the operators T and S were given by a finite procedure that only uses vector addition and scalar multiplications, and then the resolvents of the maximally monotone operators allowing different step size parameters. Okay? So this is basically the same thing that Malitsky needed, but just adding the resolving parameters. And then we also you usually also require that your method to be frugal, which means that at every iteration you use the resolvent of each one of the operators exactly once. And this makes sense because, as I said before, like resolvents are difficult to compute, so you don't want to evaluate lots of them, okay, at the same time. So then what we got is that we could extend Malitsky and Tamp results to say that when you consider a frugal resolvent splitting, then the lower bound is still n minus 1. Okay? And then this means that, for example, one of these algorithms that I said, which is Campoy's product space reformulation, that was previous to the result of Malitsky-Tamp, we could also guarantee that it has minimal lifting. Okay. So how much time do I have left? It's like 10 minutes? 20? Oh, okay, then I'm good. Okay, so then actually the reason why we actually added these resolving parameters in our result was because we were in fact we were interested in this other monotone inclusion problem, which is the composite monotone inclusion. So I will be a bit fast here, but if you are interested in this, you can check my thesis where I did like added not only these 2 monotone inclusions, but more monotone inclusions problems. So you can go and check them if you want. And the problem that we wanted is the following. So we now have n maximally monotone operators, which is this A here, which are defined in the same space, but then we have other m maximally monotone operators, which are the B's, which are defined in different spaces. And the problem that we want to solve is to find a 0 of the sum of the operators, which I am going to call primal, and then these compositions of the operators B with some bounded linear operators and their adjoints. So this is the so-called composite monotone inclusion problem. And this is significantly more difficult because here, these operators here, these compositions are not maximally monotone anymore. So you need some more rules when you define algorithms to address this problem. The first one of them is that there is one dual problem associated to this one, which is this ugly guy here that you also want to be able to solve. And the thing is that this is just just to say that these two are the problems that you want to solve if you are interested in addressing the minimization of convex functions, of sum of convex functions where some of them are composed with some linear operator. Okay? So then the class of splitting algorithms that are used to address this problem are called primal dual splitting algorithms. And as I said, there are some things that you require in order to have a good splitting algorithm, and it's the following: that you want to solve both the primal and the dual problem simultaneously. So then you need variables on both the primal space and the space and the dual space, which, as you can see, is the ones given by these maximally monotone operators. Okay, so you need two sequences: the sequence of primal solution and the sequence of dual variables. Okay. Then you want to use only the resolvents of the maximally monotone operators, and finally the linear operators should only be evaluated with forward evaluations of them and their adjoints. So you don't want, for example, any kind of inverse, because those are difficult to compute, okay, and are not good in practice. So probably the most famous algorithm to address this problem is the Chambol-Pock splitting algorithm. So going fast, it takes this form here, just saying that, as you can see, there is one sequence is given by the primal variables, this in H, but it also considers a second sequence, which is a dual sequence because it's in G, the space of the linearly composed operator, and then it does evaluation of the maximally monotone operators. There is an inverse here, but this is equivalent of computing the resolvent of P. And then you only have forward evaluations of the linear operators and the adjoints. Okay, so this is the result that you can both the primal sequence will converge to a solution of the primal problem, and the dual sequence will converge to a wiggly to a solution of the dual problem. So then we wanted to study the minimal lifting of primal dual splittings, and we needed an additional definition, which is this primal dual lifting, which also takes into account this nature of having both a primal and dual sequences. So given a fixed point encoding, we said that it has df for lifting, which d is going to be for the primal variables and f for the dual variables, if both the fixed point operator t and the solution mapping are evaluated in this product space here, which has d copies of the primal variables, and then the total number of copies of the dual variables is the sum of all these exponents. This is that you have f copies of the dual variables independently of which space they are. Okay. So with this definition, what we could prove is that given a frugal primal dual resolvent splitting for the composite monotone inclusion that has dm for lifting, this is we are fixing the lifting of the dual variables to be the same number of the maximally monotone operators that were composed in the problem. Okay, so we need that. Then what we have is that with fixing this dual lifting, then the minimal lifting for the primal variable has also to be n-1, which this is the number of maximally monotone operators in the primal space minus 1. Okay. Well, I'm gonna skip that. Okay, so it turns out that there were several splitting algorithms that were used to solve this problem with more than 2 operators there, and it turns out that all of them had NM for lifting, so they didn't have minimal lifting at all. So what we also did was we gave a primal dual resolvent splitting, which is the first one that has minimal lifting for this problem according to this definition. And as far as I know, this is the only one that I know so far. Okay, so for other problems there have been more methods, but for this problem, I think ours is the only one. Okay, and just to conclude, I just want to give some numerical examples. So Okay, this is a picture that I took in Vienna that you saw before, and it is blurred and noisy. So we want to recover the original one. And this can be done with the problem that I wrote in the first slide. So yeah, I think I'm going to skip also again the definition of this, but if you are interested, you can ask me later for the questions. So, but the thing is that this problem here can be written as this composite monotone inclusion, the last one that I presented, where I have two maximally monotone operators and two maximally monotone operators that were linearly composed. Okay? So in order to solve this problem, one illustration of what our algorithm can do is, so you have here the blurred and noisy image that we consider for the experiment, and this is going to be the restored after some number of iterations. Now it's 0, so they are the same. So if I do 10 iterations, this one is changing and it's improving, and it's getting better with the iteration, and we stop at 400 iterations, and this is the recovered one. And if you compare with the original one, I think that probably here in the projector you wouldn't be able to see the difference, because I think the model is quite good, this one. Okay, so the algorithm works well. So what happens if I compare my algorithm with minimal lifting with one algorithm that doesn't have minimal lifting? Okay, so this is what I'm going to show now. So I ran 400 iterations of my algorithm with minimal lifting, which is the red one, and then this other algorithm which didn't have minimal lifting. So the plots show the X label are both the CPU time in seconds, and then in this one I'm showing the Y label, the objective function. So you are minimizing, so you want it to be smaller, and you can see that more of the methods get minimum the same objective function value. And then in this one, the Y label is this measure here, which is some measuring the quality of the recovery. So the highest, the better. Yeah, and you can see they are also very similar, but our method is a bit better, okay? So the red one is better. But the important thing here is that actually the thing is that I'm running 400 iterations for both of the methods, but if you see the time, the blue line has to go until more than 400 seconds, but our method stops way earlier, after 200 seconds, yeah. So I think it was like almost 40% faster. So, and this is at least the conclusion that we could draw from our experiment, and is that this reduction in the lifting is being useful for, while keeping the same quality of the recovery, getting like a more efficient method that can perform the same number of iterations in less time. Okay. Yeah, so this was all I wanted to say. Here are some references here. Yes, so thank you for your attention. Yeah. Okay.
Questions for the speaker?
Thanks for the talk. Another kind of splitting algorithm would be ADMM, where now you throw in some equality constraints in addition to the proxies or the functions that you need to minimize. Can that be put in this framework, or with the equality constraints?
Yeah. I'm not sure, actually. I think there is some connection, right, between ADMM and Douglas-Rashford, right? So yeah, I guess that maybe there should be some connection, but I don't know if in this paper of Malitsky and Tam, I think they also work a bit with ADMM, but not really sure what kind of result they got. So yeah, it's a very good question, but I'm not sure right now.
You can't use the indicator function to put the equality constraint up in the objective?
I mean, yeah, I think that's usually what I'm doing here. That's what I'm doing here. But you mean in ADMM or? Yeah, but then I don't know if you. Yeah, I'm not. Yeah, I'm actually not super familiar with ADMM, but yeah, maybe. Yeah, I'm not sure right now. Yeah.
I have perhaps a silly question. Why is your lift always multiples? So for example, like if I have a problem in 10 dimensions, you're saying like, oh, either I solve in 10 or 20 or 30. Like why couldn't I have like the iteration on like 13 or 15? Why you demultiplies your dimension instead of like just lifting for a smaller number? Is it easy to see why it must be that way?
I'm not sure if I understand the question. So, what?
So you defined your lift of the
Yeah.
representation as like how many, like you're multiplying your dimensions. So like if you're solving a problem in 10 dimensions, if the D is 2, you got to go to 20 dimensions to solve it in your algorithm. Or did I
No.
misunderstand?
Yeah, so actually, so if you have a problem in dimension 10, you have a variable in dimension 10, and then you need like another copy of the whole variable, yes. So you mean that if I can only like half of the variables?
Yeah.
Yeah, I don't know if that can be done because actually what you are like, because it is like the variable is your function, right? So for example, if the function is defined in R10, you cannot, for example, use that function and defining it in R15 or something. So it's, I'm not sure if, I don't think it's possible, like, at least not with this approach. Yeah.
I see. Thank you.
Okay, thank you for the question.
Thank you for the talk. I'm assuming throughout the presentation you're assuming that this set of zeros is non-empty.
Yeah.
And so one question I wonder if, do you know the behavior of the splitting algorithm when there's no zero
Yeah.
exist, and does it diverge? Does it, like
Yeah.
what happens in it?
Yeah, as far as I know, I'm familiar with, I've seen some of those papers, but as far as I know, for these other methods with minimal lifting, I don't think that has been studied. So,
Oh, it has not been studied.
yeah, I don't think so. I don't know, for example, for the method that I propose here, I think at some moment I tried to check something about that, but I didn't get too far. I don't know if it's too difficult or what.
Okay,
Yeah.
thank you very much.
Any other questions?
For the image recovery problem,
Yeah.
what if you went past 400 iterations? I mean, a lot of these problems can be over-parameterized, so the picture becomes good, and then if you continue, it usually
Yeah.
becomes bad again.
Yeah, from what I've seen, usually for these kind of problems, you fix the number of iterations, like you run your algorithms until some number of iterations, because if you continue and let more iteration, then the solution gets worse. Yeah. So I think.
know when to stop.
Yeah. So I think the usual stopping criterion is the number of iterations. Yeah. So I think that's related. Does that answer your question? Yeah. I don't know what. Yeah. I think that if I let more iteration, it would get worse. Yeah. I think so.
All right, let's thank the speaker.